this part of the introduction will be a much more technical talk than the first one, so there will be many technical details. So if something is not clear, please ask. So there will be, I assume there will be people from many different backgrounds here. So some people might know some things and other people might know other things. I can't go into all detail in 45 minutes. There are much too many things to tell about force fields, thermostats and barostats and everything. So I'll try to stay in time. But if something is not clear, please interrupt. So the first question is, what is a force field? Since you could have many different systems, different way to treat them. So what I'll discuss today is what's a force field in the context of Gromacs mainly, and in biomolecular simulations, which most of the people here will be interested in. But you could also think of coarse-grained force fields or other kind of systems which might come up later in during this meeting. But for now, I'll talk about the general force fields that we have in Gromacs. So for force fields, what does a force field consist of? We would usually think of three different things in this context here. So there's a set of functional forms which describes how the interactions between the atoms and so on in the system look like. Then there are the parameters for these functional forms that would usually depend on the atom types that you set for your system. And then a third thing is a set of building blocks, which could be, for instance, building blocks for amino acids. So this means that if you would want to simulate a protein, you don't need to build up the whole protein by yourself, assign everything, but that if you have building blocks for them, it can be automatically generated, and you'll have a properly set up force field for your protein automatically. Okay, so what Gromacs supports, that's the in general is something that looks like is drawn here or written here. So we can split a force field into two main contributions. One is bonded interactions that only work within molecules, that work on short distance along chemical bonds. And the other part is non-bonded interactions that work between molecules, but also within a molecule on longer distances. So in the current setup of Gromacs, we can have bonded interactions within molecules, and we can have interactions between two particles, between 3 and 4. So the two will be bonds or pairs, which I'll discuss later what that means. We can have angles, we can have dihedrals, which work along 4 atoms. And then there are the non-bonded interactions, which in principle is a sum over all pair of atoms in the system, but where you use a cutoff, as has been explained already by Eric before. So first, the non-bonded interactions. So what Gromacs supports at the moment is pairwise additive and centrosymmetric interactions. So for the electrostatics, these are determined by the charges you set for the particles, and this is just a Coulomb interaction. That's what you would usually use, but you can also have a user-determined tabulated interaction where the distance dependence can be set by the user if you want to have something different than plain Coulomb interactions. The other type of interactions are van der Waals interactions, which Leonard-Jones has been shown already by Eric before. Again, here you can also have tabulated interactions where we now have two tabulated functions that can be set by the user to have any type of interaction he likes with 2 different parameters in here. Or we can have a Buckingham potential which has an exponential in here, but this is, in biomolecular force fields, is not used very often, but it's supported by Gromacs. So for the bonded interactions, there are many choices. So first there are the bonds, which are the chemical bonds in your system, which is a 2-body term. So you can have a harmonic term here, which is just where you take the square of the distance between 2 particles minus the equilibrium distance, and you have a force constant in here. But you can have, I don't know how many types we have now, 6 or 7 different bond interactions in Gromacs, depending on whatever force field you want to use or what you want to do. So here's an example of a fourth power bond stretching, which Gromacs has put in to make it cheaper to calculate the interaction, but actually this doesn't matter too much. Then there are angles, which are 3-body terms, so that's for the angle bending, as has been shown by Eric before. Here you can again have the most common one is the harmonic angle potential, but there's, for instance, also a cosine angle potential to save you from calculating the arc cosine, and there are many more also in this case. But instead of bonds in Gromacs, we would usually use constraints. So that the bonds don't vibrate, but the atoms that are connected by a chemical bond are put at fixed distance. Now, why wouldn't you want to do this? So this is actually a more faithful representation of reality, since the dynamics of bonds, which vibrate very rapidly, are of quantum nature and will not be treated correctly by a harmonic spring or anything classical. And another important advantage is that if you remove these bond vibrations by using constraints, you can take a time step which instead of half a femtosecond or 1 femtosecond will be now 2 or 4 femtoseconds. So this gives you roughly a factor of 4 or something like that in time step, which means that you need to wait, instead of 4 weeks for your simulation, you only need to wait 1 week, for instance, which is very nice. So this is actually an advantage of Gromacs over some other packages, or most other packages, I guess, because most other packages would not allow you to constrain all the bonds in the molecule, but for instance only the bonds concerning hydrogen atoms. So then if we go on with the bonded interactions, there are improper dihedrals, which have been shortly mentioned by Eric. For these are to keep, for instance, rings planar, or to keep the stereochemistry as you want to have it, because if you have a stereochemical molecule like a protein, for instance, you would like to have it stay the same and not turn into its in the other state. These are just harmonic potentials. Then there are improper let's see, oh, I made a typing error here. This should be proper dihedral. So this is a four-body term which is for the dihedral, for the torsional twistings in your system. Here again, there are many choices. Here I list a few. So this is, for instance, a single cosine potential, the simplest one, which is just a cosine, and you can choose the how many maxima and minima you want to have in there. There are more complicated terms like Ricard-Bellemans, which has 6 terms in here, so you have more freedom to adjust the potential to what you would like to have it. Then there are the tricky 1,4 interactions or pair terms. So these are terms that concern the atoms at the end of a torsion. So the 1 and the 4. I'll go into that later. So these are, depending on the force field, normal Lennard-Jones interaction, or scaled down, or normal Coulomb, or scaled down Coulomb. So I'll go into that later. So for a dihedral, which has been shown already shortly, it's just describes the potential as a function of the rotation around this dihedral, which for a very simple case could just have 2 minima like this, and it's periodic around here. And then, but then also the interaction between I and between sorry, it should be L here. Between the first and the last atom, they also contribute to this, but to the potential around if you rotate this thing around, also interaction between this and this atom will change. So you have to take that into account. But more on that later. So then there are improper dihedrals, which are to keep rings flat, for instance. So you can draw a triangle here. You can draw a triangle here between these 3 atoms, and then you want to keep the plane between these. You want to keep these 2 triangles in the same plane. So there's a harmonic potential to do this. Then there's things like keeping this structure here planar, or to keep a tetrahedral structure tetrahedral. Let's see. Sorry. So then some words on the choice of force field. So the choice of force field is one of the most important things in simulating. So there are, as Eric has told, there are actually only 2 things in simulation if you at least set up the other details like cutoffs and so on right. There's a starting structure, which will determine your outcome, and the choice of force fields. Once you've set those 2, except for the system being chaotic and you not being able to sample enough, as had been discussed, if you could sample enough, these 2 things would determine what happens to your system. So the choice of force field is very essential, because it will determine the outcome of your simulations. So in order to trust your results, you need to choose a force field that is proper for your system and that you can trust. So if you can trust the force field, it depends a lot on what you want to do with it, which properties you would like to get out, and how much work has been done on these force fields and those properties that you want. So it's beforehand quite difficult to say what is good in which case and so on. So you have to gain some experience on this, and maybe after, if you're lucky, you will have a good force field. You choose the right force field right away, but it can take years to have some experience and some feeling what a force field could do and what it couldn't do. So as I've written here, a good force field, or biomolecular force field at least, which is able to treat proteins which have many different chemical units in there, it requires years of work by many people. And then all the parameters, the main problem is that all the parameters for all the molecules should be consistent with each other, so that if you throw all kinds of different molecules or chemical groups into your system, they should behave well, and not that one molecule immediately sticks to another one or repels it, whereas it shouldn't. So this is difficult work, nasty work as well. I mean, usually if you're a PhD student, I mean, when you start, you might not know about this, and you might end up in here, but you should try to avoid these kind of topics. So it's very important work, but I mean, whole group can work on this, so you can work for years on just deriving a few parameters and not getting any real results, so to say. So what you end to get out is just a set of numbers that other people can use to simulate then. Okay, so if you have a system and you want to simulate, you have to choose a force field. So the first question is, which of the force fields have the parameters for the molecules that are present in your system? So, of course, if only one force field has the parameters for your molecule, and the force field is reasonably reliable, which is again hard to judge, then you should choose that one. So, but there can be a problem that there are no parameters for your molecule actually. So what should you do? Well, the first thing is search the literature. Some person might have done maybe 10 years ago simulated this system and came up with some parameters. Then you should of course check if they're reasonable or not. So if you're lucky, they are, and you can use them. So if not, then you have to do force field parameterization yourself, which is bad. You just waste time is a bit too much said maybe, but you have to do a lot of work and hope that you come up with reasonable parameters. So what we have in Gromacs at the moment, in terms of force fields, so we have three main force fields. So there's the Gromacs force field, and then 6 versions of this actually. This is a united atom force field, which means that the aliphatic carbons have the aliphatic hydrogens on one side. So there are no explicit aliphatic hydrogens in the system. All the other hydrogens are there. So all the hydrogens that have significant charge are present in the system. Then we have the OPLS all-atom force field. So this is all-atom, has all the nuclei in it. And then there's amber, of which there are 7 versions currently, also all-atom. Amber is not in the current distribution, but it's available via this link, which you'll also find on the Gromacs page. So what are these force fields good for? Well, all of them are biomolecular force fields, so they have been initially mainly developed for proteins. So if you have a protein to simulate, you actually have the choice between all these 3. And which one of those is best in that case is very hard to say. So a lot of work has gone into all these force fields, and some might be slightly better at these properties, some slightly better at others, but I would say at the moment they're probably all 3 roughly equally as good on this aspect. Then hydrocarbons. So in Gromacs, they've done a lot of work to correctly represent hydrocarbons, also in OPLS. So these 2 force fields are a good choice for hydrocarbon simulations, where actually Gromacs is probably computationally the better choice because of the united atoms. So in this case, you will have, if you have a long hydrocarbon, it has CH2 groups in there. So this will have 1/3 of the number of nuclei of this one, which will give you a factor of 9. 1/3 squared in computational time that you save here. Then OPLS additionally has many liquid parameters in there. So if you have simple liquids, or you need to solvate a protein or something else, in OPLS there's a reasonable chance that you have those systems in there. And then the important DNA and RNA for many biomolecular things. I think at the moment amber is still the only force field that does this properly. So there are people working on this for other force fields, very hard at the moment, because as you know, I mean, DNA and RNA are very important systems to consider. So actually, I don't know, maybe there are some things in Gromacs as well on this, but at the moment I would say amber is the only force field to trust there. So if you have that, you have no choice but to use amber. Okay, then if your parameters are not present in a force field, you might need to parameterize them. So the first things, you might need to parameterize charges or Lennard-Jones parameters. So this is very tricky, I should say. It might seem easy. I mean, you can easily come up with a charge, of course, but the question is, if I put a nice charge into a force field, what will happen? Will my molecule stick far too strong to another molecule, or will it stay away, whereas it shouldn't? So the way to do this is to try, if you want to derive charge in Lennard-Jones parameters, try to do it the same way as the force field has been parameterized. So you have to look in the literature on the force field that you want to use and see how they came up with these parameters, and try to do it in the same way such that your parameters are consistent with the ones in the force field. So this also means that there's not one set of best parameters, as you might think. You might think this is a molecule. There's only, if I do a quantum calculation or so, there must be one best set of parameters. It's actually not the case, because the force fields might have been parameterized in different ways. Some force fields might have higher charges than other force fields, which are compensated by Lennard-Jones terms. So you have to make sure that these parameters match the ones of the force field that you want to put them into. So then the other thing is bonded terms, bonds, angles, dihedrals. Dihedrals are often things that you need to do. So this is relatively easy, because from quantum calculations you can nowadays, without too much effort, you can get these parameters. But you have to be careful about the 1,4 terms, as I mentioned before, so I'll show now how that works. So say I have a dihedral here, so I have this bond between C2 and C3, and the groups on the sides so these groups can rotate with respect to each other around this bond. So how does this look how is this parameterized in the force field? So as far as dihedrals terms can, so these are these cosine terms for the angle, how they can go. So there's two different options. So many force fields have all possible dihedrals around here. So you can have C1, C2, C3, C4, but you can also have, like here, you can have H21, C2, C3, C4, and so on. So you can have 9 dihedral terms in total. Or you can have just one. The Gromacs force field would only use the one along the heavy atoms. So that's one part of the torsional potential here. The other part is the 1,4 interactions. So these are interactions, as they say, between atom 1 here and atom number 4. And there are always 9 of these, so between all the different pairs on this side and on this side. So the original idea behind this way of parameterizing it is that the dihedral potential gives only the dependence of the middle 2 atoms, whereas the 1,4 terms give the dependency on the outer atoms here. So you do not need to parameterize dihedrals for all different combinations there are. In practice, however, these things have been fine-tuned. So actually, in the OPLS force field, you would find these 9 dihedrals wouldn't be all identical. They might be slightly different. So if you need to parameterize something like this, what do you do? So you can do a quantum calculation, for instance with Gaussian. There's a functionality in there to scan the dihedral. So you put in a small fragment of your molecule where the dihedral is in there. Then you can scan the dihedral in steps of, for instance, 15 degrees. You can turn it around, optimize all the structures, you get out the energies. Then you can put these structures, you can put them into Gromacs using the rerun option of MD-run, which we'll see later on. Then you can get out the force field energies of the system. So if you do not put in the dihedral that you actually need to parameterize, the difference between the quantum and the force field term would actually give the term you need to have. But the important thing here is to put in the 1,4 interactions, because people often forget this. And if you do this, so you first parameterize it nicely, then you put it in the force field, but you forgot the 1,4 interactions, you count them double, and you get a wrong result. If you check your results at the end, you'll find it, but force field errors can often be very hard to track down. So then I'll come to the way these things are put into Gromacs. So you'll see in the exercises, you'll see some examples yourself. You can look into this. So I'll describe now how this works. So the topology, all the details I told you are all stored in the .top file, the topology file. So this topology file includes the force field, which are all the parameters for all your system, and these are stored in a directory in the Gromacs, where Gromacs is installed on your machine. So if you have a protein, then this whole topology can be generated fully automatically from the force field building blocks using the program PDB2GMX, which I guess is also what we'll do this afternoon. So now we'll have a look into the topology file. So here is a topology file for methanol. So in this case, I've taken an example of the Gromacs force field. So the Gromacs force field file is this file here, which is included here in this way. For people that program C, they might be familiar with the include statement. So actually, the Gromacs topologies are parsed through the C preprocessor. So you can include files and so on. It works the same way as a C program is preprocessed. So we don't need to write the whole force field here. You can include things here, so you can add your own files as well. They'll be included if you put a statement like this. So then you can have a definition of your molecule, which I'll come to on the next slide. Then you can, for instance, here include another molecular topology, like here is SPC, is a water topology for the water model. So you can include this file here, which is already in the Gromacs directory. Then there's the system directive here, which tells the name of the system, not more than that. And then there are the molecules in the system. So in this case, I've put, for instance, one methanol here. So this methanol is the same name as here. That's the molecule type. And then there's sol, which is actually the solvent, which is defined here in this water topology file. So this is what you'll have in general when you simulate a system. So in this case, as I'll show you on the next slide, the molecule block is quite small, but if you have a protein, you have something very big here, which defines all the interaction in the protein. Now we'll have a look at how this molecule is defined. So for methanol, so there's the name of the molecule, then there are the number of exclusions, which are given by the way the force field is set up. So this actually means that I exclude interaction between 1 and 2, so that's directly bonded, between 1 and 3, which is then along 2 bonds, and along 3 bonds is the next one, is the 1,4 interaction. Those are excluded, and the 1,4 interactions are put in separately afterwards. But this is a number that you'll have to find out from the force field, but I think for all current force fields in Gromacs, it's always 3. Then for methanol, so we need to define the atoms in the system. So methanol has, in this case, because I chose the Gromacs force field, it has 3 atoms, because there's a united CH3 atom in here. So you have on the line for the atoms, you first have the atom number, which has the number consecutively. It always goes 1 to 3. Then there's the atom type. So this refers to the type in the force field. So depending on what kind of carbon it is, you can have different atom types, because in a different chemical environment, carbon can have different interaction with other atoms. So in this case, this is a CH3 type here. Then there's the residue number, which is not so important for a small molecule, but for proteins you would have I mean here it's all 1 because we consider it one residue, but actually this number has no effect on the computation. It's just for analysis purposes that you can easily select residues. Then there's the residue name, which is also only for selecting things, doesn't have influence on the computation. The atom name, also only for selection. Then there's the charge group number, which refers to in which charge groups these atoms are, which Eric has mentioned. I'll mention that later as well. Then there's the charge of the atom and the mass of the atom. So these are defined now for all the 3 atoms. You have this here. Then there are the bonded interactions. So the first one is bonds. So here's a bond between atom 1 and 2. So that would be these 2 atoms here. There's a function type, which depends on the force field. In this case, since it's Gromacs, it's for function type 2. So you have to know these. If you make a topology by hand, you have to know which function types to select. And actually here, the parameters are given explicitly in the topology. This is a peculiarity of the Gromacs force field. For most other force fields, actually, if you know the atom type, the force field would give you the parameters, which is easier. In the Gromacs force field, you have to put them in by hand, which is a bit nasty, but that's the way that the person designing this force field chose to do. So it makes life for us somewhat less easy. Then there's, for instance, angles. So here you would have an angle between atoms 1, 2, and 3, also function type 2, and the parameters, which are, in this case, by the C preprocessor, these strings are replaced by the parameters. Okay, then we can have a look into the force field files. So this is, here on top I show something for the Gromacs force field. So we define some strings to be able to, later on, if we need to do things specifically for a specific force field, we can do that using the preprocessor. Then there are some defaults for certain things, like this tells tells something about if we have van der Waals interactions or Buckingham. This tells something about how we need to combine the Lennard-Jones parameters between different atom types. This tells something about how to generate 1,4 interactions, and this tells how the 1,4 interactions are scaled, which are not scaled for the Gromacs force field. So these are things that are given by the force field. You don't need to edit this, but it's useful to know what happens here. And then there's files included. So these are the non-bonded parameters, NB, and these are the bonded parameters. We'll have a look at those files later as well. So here on the bottom, there's an example for the OPLS force field, which is analogous to the Gromos thing, except that here, for instance, there's a different combination rule, since in this case we read sigma and epsilon parameters. There's a different pair generation, and there's scaled Lennard-Jones interaction between 1,4 atoms. So then if we look into the other files, so this is the definition of non-bonded interactions. We can see that, for instance, for OPLS here we have defined different atom types, and then it gives the bonded atom type for this. In this case, you have the mass, the charge, and the Lennard-Jones parameters, which are the most important in this case. So this defines all the interactions between the different atom types in the system. Then if we go to the bonded, if we have a look in the bonded file, there are the bond types. So this tells for instance, if I have a bond between an OW, which is a water oxygen, and a water hydrogen, it should have this bond length and this strength. And the same for angles, you have 3 atom types. And you can have wildcards here, for instance. So this was between all types of carbons and a hydrogen connected to a carbon, you have these parameters. So these is the equivalent files for the Gromos force field, which are here similar for the non-bondeds. But here actually in the Gromos force field you need to define all the different combinations of the different atom types, all the Lennard-Jones parameters, and the same for the pairs. A lot of work, which you don't need to know, but it's not nice to know that it is all in there. Then the bonded parameters of Gromos, these actually, so here we use the C preprocessor command define to define the bonded interactions, and then you have to know if I have a molecule and I want to have I need a bond between 2 atoms, then you need to look by hand in this list to see which parameters you should choose. If you have a protein, again, this is done fully automatically. But if you have something else you need to do it by hand, you have to look. Okay. So how to make topologies? So for protein, you use PDB to GMX. Everything is magically done for you. If the protein structure is done properly, but often there will be problems in there, like the crystallographers might have two different, might have seen two different densities for one side chain. There might be then doubles atoms in there and all kinds of things. So this can be complicated. But in principle, you don't have to worry about writing all the topologies. So for small molecules, you can write a topology by hand, but you have to be very careful about the details of the force field, as I've told. Now for other kinds of systems, like you can have polymers, it might be good to write a building block by hand. So I won't go into the building block files here, but you can write a building block by hand, and then because a polymer usually consists of very small units, so you only need to define one small unit, and then PDB to JMX can, just like for a protein, it can generate a whole polymer topology for you to make life easy. Okay, then the next subject will be thermostats and barostats, which Eric already mentioned shortly. So if we do plain MD, as Eric showed, just Newton's equation of motion, we have Hamiltonian dynamics, and this conserves energy. So then we have a constant number of atoms, constant volume, constant energy simulation. Whereas you usually would not want to have this because you want to simulate at a constant temperature, not at a constant energy. Unless you have very specific needs, like David here wants to do constant energy simulations, but it doesn't occur very often. So what you usually would want is a constant number of atoms, constant volume, constant temperature, or a constant pressure instead of constant volume. So to achieve this, the equations of motion need to be modified because this plain MD will give Hamiltonian dynamics, so we need to do something about that, and this means including a thermostat or a barostat to keep the temperature or the pressure constant. So first I'll talk about thermostats, and there are 2 different types. There are global thermostats and local thermostats. So first I'll show the global thermostats that Gromacs has. So one of the popular ones is the Berendsen thermostat, which couples weakly to above is the idea. So the idea is that if you have a temperature T that deviates from the real temperature that you would like to, for the temperature you would like to have, T0, you slowly couple it with a single exponential decay, first order decay, with a time constant tau, so that it relaxes to the temperature you want. So to achieve this, you can scale all the velocities with a factor lambda, which is written here in this way, which contains this tau here, and then this will work out. So you set this tau in the MDP file. And then you can have, if you would like to have, you can have different temperatures for different subgroups of the system or different coupling times, which is a bit exotic, but if you want, you can do these kind of things. The problem with a Berenson thermostat is actually that you cannot prove that actually I think it's even worse, the system will strictly not generate an ensemble. So you modify your equation of motion, but you don't know exactly what will come out. In practice, this is not really a problem. So for a big system, you usually will not have any big deviations from what you would like to have. But if you want to have a proper, strictly defined ensemble, there's another global thermostat, the Noether-Hoover thermostat, which has been proven to give the correct ensemble. So in this thermostat, we extend the ensemble with another degree of freedom. So we add a degree of freedom to the Hamiltonian, and this is then coupled in this way with these degrees of freedom. So then you can prove that this extended Hamiltonian is canonical, but the original system behaves NVT. And you need to set a mass, but actually in Gromacs you need to set a period. So the disadvantage here is that you can get oscillations like I've shown here for the, I have a box of water at 300 Kelvin, I increase the temperature to 330 Kelvin, then actually for the Noether-Hoover thermostat you get this red line which goes up and down, oscillates, but for a Berenson thermostat you would get a nice exponential behavior. Another point is ergodicity. So global thermostats only work well when all degrees of freedom in the system are coupled strong enough to one another. If this is not the case, then you can get strange effects. Like here, I've shown a small picture for if you would have a slab of water and a slab of octane in your system, the interaction between water and octane are very weak, and you can actually have that the octane slab will start moving with a velocity with respect to the water slab. This is not what you want. So you can get temperature differences as well in between these two slabs. So a solution for this is separating. Have separate thermostats for the octane and the water, and then you have to do something with the degree of freedom between the water and the octane, which in Gromacs will be kept fixed in that case. For a simple system like this, that works, but you can have more complicated cases where you cannot solve it this easily, and there you would need to have a local thermostat, a thermostat that works locally in each degree of freedom. So here you can use stochastic dynamics. So what actually happens here is you have the same equation. Newton's equation would just have this term and the force, but you add a friction term here. So this is a minus a constant times the velocity. So you have a friction, and you add noise. And if you choose the friction and the noise properly, you get the proper ensemble. So this has the advantage that it's a proper ensemble. It's always ergodic, so you don't have problems that you have decoupled degrees of freedom which get different temperatures or which are not sampled properly. There are no oscillations. But the disadvantage is that all velocity correlations decay with an exponential, which in some cases can be problematic, in other cases not, so that depends on the system. Then you can also have an overdamped limit where you get Brownian dynamics, which is where the velocity is just proportional to the force directly. So this is not useful for dynamics since everything is very damped, but it can be useful for equilibrating bad starting structures. Then barostats. So this is analogous to the thermostat. You can couple the pressure. So this is a Berenson one again, where you would have the exponential decay, which is achieved by scaling the box and the coordinates in your system with a scaling factor, which is written down here. Or you can have an extended Hamiltonian approach again, which would be the Parinello-Raman barostat, which has been proven to give the correct ensemble, I think. Okay, then the last thing, I'll go a bit into detail on how the non-bonded interactions are calculated. So this is the most time-consuming part of MD. So you can make different choices here depending on what efficiency you want, what accuracy. So it's important to have an idea what how this is done and what kind of things you have to think of here. So in principle, for a periodic system of n atoms, we would need to have determine n squared, or actually exactly is this number, n squared pair interactions, but actually many more interactions. Since the system is periodic, you would also have to calculate all the interaction with all the periodic images. So there's an infinite number of interactions. You don't want to do this, of course. So for that we use cutoffs, as Eric has explained before. So what happens in Gromacs? So we construct a list of close neighbors, and we keep this fixed for n steps. So how the algorithm runs then is we construct a neighbor list for all charge groups. I'll show a bit more about charge group later, within a cutoff radius. So then n times we evaluate the potential and the forces for all these pairs that we have in the list, and we integrate the equation of motion. So we do this n times while keeping this list fixed, and then we make a new list. That's because making the list is expensive, so you don't want to do that too often. So this is done with charge groups, as Eric had already mentioned. So we use this because of two reasons. Well, one thing is the efficiency of the neighbor search. So if we have two water molecules, if we have, in principle, we have 9 distance pairs, 9 distances to calculate. But if we use the center of mass or center of geometry of these two water molecules, we actually have only 1 distance to calculate. So this is cheaper for the neighbor searching efficiency to group these atoms together and only look for distances between whole water molecules and then put all the atoms in a list. The other thing is that we avoid electrostatic artifacts due to cutoffs. If I would have a cutoff, so for instance this positively charged hydrogen would have this cutoff distance, and it would see a positively charged hydrogen here, and the water molecules would repel each other. But actually you can see that you have two dipoles here which are oppositely aligned, so they should attract each other actually. So if you make a neighbor list and you only put whole water molecules in a list, then these two water molecules would see each other as dipoles, which would reduce the artifacts. But actually the charge groups give a problem here. So here I've drawn if I have this molecule here in the middle, which would be one charge group, I make a cutoff. Then you can see that all the black molecules are seen by this one, but the white ones are not. So you can actually see that this white one, which sticks in, is quite close, but its center is slightly outside. So you can have atoms that are close, that are not seen, or atoms far away that are seen. So this is you have to make a trade-off here in accuracy and in efficiency. So if the molecule moves and we keep this list fixed, you can see that this molecule has now moved a bit in this direction, others have also moved, so their blacks have come closer, further away, but actually, for instance, a molecule here can, which wasn't seen, can have come even closer. So you need to somehow balance these things, and you need to update this list in time again to not miss important interactions. One solution here is actually would be to search in this big radius, but actually only calculate interactions in a small radius, so that you avoid seeing other molecules too late. But then you have to modify the interactions, which can be done. So this is one of the options. So you see now that here in the second picture, the white molecule hasn't entered the interaction range yet. The electrostatics have been treated by Eric, so I won't go into those details. One more thing here on Lennard-Jones interactions. So this picture has been shown also by Eric, that this Lennard-Jones interaction decays very rapidly to 0 here. So it decays as 1 over r to the 6th. But actually, so for pairs, the interaction can be very small already at 1 nanometer, for instance. But in total energy, it can still contribute because there are many more pairs at long distance. So you can calculate what this contribution will be. So if we integrate from the cutoff, say RC, the cutoff to infinity, this 1 over r to the 6th, you would actually get an 1 over r to the 3rd term, which can still be important depending on the properties you're interested in. So to take this into account, one can calculate an average interaction strength and just put in this analytical term here beyond a certain distance. So this will take an average dispersion into account, but you will not have specific differences, which for a membrane system this might not be a good idea, but for a system in water where there's water everywhere, this can be a nice way to treat longer range Lennard-Jones interactions. Then box shapes have already been shown by Eric, except that you didn't have the rhombic dodecahedron in there, but something else. But my picture is also not very good. So, let's see. Yeah, some details of the neighbor searching. I don't know how important this is, but it might be nice to see once at least how we do this in Gromacs. So if I have a particle I here. How do we calculate which neighbors this particle sees? So first, what we first do is we put all the particles in the cell. We put in the unit cell. We put on a grid. So here I've drawn a grid of 8 by 4 squares in 2D. So each particle is put into a cell. So if I have particle I here, I know from this by drawing this radius that it only sees these cells which are drawn here. So I only need to look for neighbors in these cells. And since I have them, I've put the particles on the grid, I know exactly which particles are where, and I can only need to calculate distances between particle I and all these particles here, not between a particle I and a particle here, which wouldn't be seen anyhow. So that improves efficiency a lot compared to calculating all the distances in the cell. And then for periodicity, this system, there's no boundary here, but it will actually see the other side. So in this case, I've drawn a triclinic cell where there are the vectors do not form an angle of 90 degrees. So if I translate this particle I by this vector here, I would end up here. So we do that actually in the code. We move the particle here, and then we also check the cells here to see. So for instance, this particle J will be seen by this position I prime of particle I. So in this way, we build up the neighbor list. Then last slide here. So we have to make, as I said, you have to balance somehow the accuracy you want with the speed, with the computation time that you want to achieve. So for some things you might want accurate, very accurate interaction calculation. For other things you might think, well, I need more time. Accuracy might not be so critical. So you need to balance this out. But there are some general rules which we can say. You should follow. So for a neighbor search in Gromacs is in C code, which is actually slow compared to the way we calculate the forces in Gromacs, which are done in SSE or Altivec, depending on the system you have, which are use very much the optimized processing in the CPUs that we have now. So calculating forces is fast, calculating neighbors is slow, but we still need to calculate neighbors. So the idea here is to calculate this neighbor, to search the neighbors not very often. So for instance, only every 10 steps, which is set by this NSC list parameter. Then the second thing, in general, I would say nowadays you should always use particle mesh ewald. In Gromacs it's quite fast, so you might, I don't know what the maximum you would save by using reaction field, maybe a factor of 2 maximal. So, but to avoid artifacts, it's often a good idea to use PME and not worry about artifacts at all. Then the important parameters are the cutoff for the electrostatic interactions and the cutoff for the van der Waals interactions. And yeah, that's basically it, but there are some choices one can make there. So if we consider the Gromacs force field, which is united atoms, so it doesn't have so many atoms per volume in general compared to an all-atom force field, I would say you should take a cutoff of 1 nanometer for the neighbor list, also for the electrostatics, and then we have a PME grid spacing of this. Then you have 2 choices for the Lennard-Jones, depending on if you need to care about differences in dispersion in your system, which is usually not, but if you have a membrane, for instance, the density of atoms in the membrane can be quite different from water. So if you do not need to care about very accurate Lennard-Jones, you can use a shifted interaction, which means that you do not have a plain cutoff, but you let the interaction go smoothly to 0, and we can correct the dispersion as I've shown you before. You take a cutoff which is shorter than the neighbor list to not have these atom charge groups going into the cutoff, and you suddenly appear. The other option is to have more accurate Lennard-Jones with a very long cutoff, which is actually longer than the neighbor list cutoff, which means that these interactions between 1 and 1.4 nanometers are only updated every time we search the cutoff. We search for the neighbors, which is, I think, a setup that not many other, well, yeah, other packages might have multiple time stepping as well, but I don't know if it's used for this. A similar thing is for OPLS, but since we have an all-atom force field here, there's a higher density of atoms, and you might want to take the cutoff shorter for efficiency, in which case you would need to make the PME grid also finer. But that's about it. So I think here in this, during the exercises, you do not need to set up these things yourself, but these parameters are usually the most important to consider. If you set up a simulation, these parameters will determine how fast your simulation runs, but they will also determine the accuracy of your simulation. So you have to make a trade-off here, and you have to think very well. If you're going to do a simulation for a week or so, you want to be sure that you don't throw a week of computation away and you use it as efficiently as possible. So you might need to also test for your own system how to set these parameters, how the accuracy is influenced. It's actually useful to, when you for your system, that you have to vary these parameters a bit and see if your results change, if your important results change, and these kind of things. So I think that's about all I could tell in 45 minutes. There's many more details that can be told, so we could go on for the whole week, I think, talking about force field details and other kind of things, but we should go on to the next part. Thank you.
Thank you very much, Berk.